Okay, determining cell potential. Now, determine the cell potential for the following reaction, then calculate the maximum electrical work of this cell when 10 grams of cadmium is used. Okay, so we can write out the full reaction here, the overall, so we can see, so this would be tin. So you should get used to taking the cell notation, which is the shorthand version of it, and putting it into this form, and then we can break it up into its half cell reactions, and you could take it directly from here if you wanted. I just wanted to show this out, and then we break it up into the oxidation, and we know it is because it's on the left hand side, and we put cadmium, then cadmium 2+. Then we have the second species reacts, and it's the reduction, so it's 2 electrons go to tin solid. Now if you look at the, I have the numbers here, but I want to double check. You have your standard electrode or standard reduction potentials, and for cadmium it's minus 0.4 for the reduction. This is the oxidation, so we have minus 0.4. Make sure that's what I have here. Yep, so this would be plus 0.4. Then tin 2 remains, that's the reduction, so it remains in the same order as in the table, so we just take negative 0.14. So overall is going to be plus 0.26 volts. Okay, and then the maximum work is negative NF E cell. And we just found E cell. We have Faraday's constant we have to put in there, and N is the number of electrons transferred. So when it's a balanced reaction, there's 2 moles of electrons transferred for this reaction. So we have N, which is 2 moles of electrons. And then we have Faraday's constant, which is 96,485 coulombs per mole of electrons. And then we have the voltage, which is 0.26 volts. So I just jumped right into this calculation. That's the equation that you'll need. 2 times. I didn't mention the conversion here, but let's do this out. And this is negative. So negative 50,172 coulombs times volts, and that's joules. Coulombs times volts gives us joules. And then we want the for 10 grams, but let's convert this to kilojoules. So it'll be minus 50 kilojoules. The minus indicates that the work is done by the system on the surroundings, which it should. That's the point of having these galvanic cells, is that they do work for us. So that has to be a negative here. Now this is got to remember that this is this much work for every what is it, cadmium? So 1 mole of cadmium. That's what we're saying here, because we had 2 moles of electrons. That's true, but 2 moles of electrons came from 1 mole of cadmium. So this is the work that the energy that cadmium gives off for 1 mole, but we don't have 1 mole. We have 10 grams. So we go back to chapter 3 kind of stuff. We say that we have 10 grams of cadmium. Hopefully I can fit it in here. 112 grams of cadmium is 1 mole of cadmium. And then for every mole, so we can then put in our energy term here. This is minus 50.2 kilojoules per mole of cadmium. That's what we said here. So when we work this through, we have 10 divided by 112 times 50.2. And this comes up to be negative 4.48 kilojoules. Now, we generally change to kilojoules just because those are easier units to work with, and to leave this as 50,000 joules, but it's up to you. That's just my natural inclination to do that. So change it over to calories if you want. Okay, so now let's do another one. Now this one I think I forgot to change, so I said when 10 grams of, silver is produced. So we'll take it from the point of view of the silver being produced. So I'm just going to go directly into the half cell reactions here because it's all set up. This is the oxidation, this is the reduction, so it's easier. Or it's easy to just shift directly over. Now, we have 2 electrons here, so 2 here, or 1 here, so we're going to have to multiply this by 2. Everything through by 2 to get the same number of electrons to match. Now, if we look at the, did I write it down here? Yeah, I want to double check. So zinc, the reduction is minus 0.76. This is the oxidation, so this is plus 0.76. We flip this, when we flip the one of the half cell reactions around, they both can't be reductions. But so the reduction potential, or standard reduction potential table has all of the information for reductions and oxidations. Any oxidation is just the, we just take the opposite sign of the potential. Now we have silver. Silver is a reduction, so we leave it as is. Where is silver? Whoa, what's down here? 0.8. And then we've multiplied by 2. So we have 0.8 here. So it might seem like since we've multiplied by 2, we multiply this by 2. But remember, this potential is for silver alone. It's a theoretical term. It's the potential for a half cell that's just on its own, sitting out there in space. No matter what we match silver against, it's going to have that half cell potential. That's the cell. That's what's going on inside its own little beaker. No matter what it's attached to, whether it's attached to zinc, which has an exchange of 2 electrons to 1, or aluminum, which would be 3 electrons to 1. It's unaffected by that. So that was really a tough thing for me to get to understand when I was going through the class. When you multiply through by 2, that will change the value of, say, delta H. Will change the value for a K, a Kc, but it doesn't change this voltage because this voltage is about silver and silver alone, no matter what it's connected to. You could connect silver to some black box, you don't know what's inside of it. The potential inside that half cell is always going to be 0.8. And so, well, we've multiplied by 2, so that should change something, and it does. It changes the energy that you get out of it because we go by the number of electrons that are transferred. So that's where the change goes, but the potential stays exactly the same. So never multiply that. And I remember that wasn't really explained very clearly in my class, and I went home and I kept being off by a factor of 2 on all of my everything that I was doing, or actually I didn't notice it because you kind of wrap it up into this number, but I was always off. Then eventually I determined that it was off by a factor of 2, and then it finally dawned on me what was happening. So I'm going to point that out before you fall into that same trap. So we have moles of electrons here, and then we put in the voltage, the E cell. So this is 2 times 96485 times 1.56. So this comes out to be minus 3. I'll just write the whole thing out. This moles of electrons cancel. Coulombs times volts gives us joules. So this, you can see that we really want to change it over to minus 301 kilojoules. And that's for 2 moles of silver. That's where that 2 comes in, because we did make 2 moles of silver to create that voltage, and to exchange 2 electrons, which went here. So the voltage wasn't affected, but that N was. We did exchange 2 electrons, which means we created 2 moles of silver doing that. So when we come through to when we want to do the or find the work done by when we produce 10 grams of silver, we had to change to moles. I think it's 108. Yeah, been using that a lot this semester. Now, for every 2 moles of silver, or 2 moles of, for 2 moles of silver, we're producing this much work. So make sure you get that, and there's that 2 again. So 10 grams of silver produces 0.0926 moles of silver. And then for every 2 moles of silver, we produce that minus 301 kilojoules of work. So that work is being done on the system. I'm going to do this really quickly again. Oops. Yeah, so that seems like the deal. Good. All right, now make sure it's on there. 3. Determine the cell potential for the spontaneous reaction between lithium and aluminum. Okay, so this requires a little, well, I have to go to the reduction potential. So write out the reduction potential for lithium. The lithium, as you see, is right at the top. And then, and because it's at the top, it's always going to be a special case, or it's going to really tells us how this reaction has to go. We'll see in a second. And aluminum, which is only a little bit further down, that's minus 1.66. Now, for it to be a spontaneous process, spontaneous means that your E cell must be greater than 0. So we know that lithium and aluminum are going to react because they're part of that table, but which one is going to be the oxidation? And which one is going to be the reduction? The reduction stays as is. The oxidation has to be flipped. Now, one of them has to be flipped every time. Even if these are both positive values, we still have to flip one. So since they're both negative here, and we need to flip one so that when we add them up, they are going to be positive, and when we flip the one reaction, we change the sign, it's got to be lithium. Lithium will always be the one that is the oxidation. It always reduces the other things around it because it has the highest value in the table. Now, there's certainly things that are above lithium as far as this reduction potential. We just don't have them in our table, or there's most likely to be. But that's why lithium is we have lithium batteries, because of this massive negative voltage that it has as its reduction potential. So we flip this around and we change the sign. So I'm going to just bring it down here. We have lithium solid goes to lithium ion and electron, and that makes this plus 0.304. So I'm going to just delete that. And now to balance it, we need to have 3, 3, and 3. That doesn't change this voltage. So here is the complete reaction. The electrons cancel, as they should. We have 3 lithium, aluminum, and then we have 3.04 minus 1.66. So this is going to be 1.38 volts, and that's going to be positive. Get right there. So determine this, since this is positive, this should be a spontaneous reaction. If we put together a galvanic cell with these components, the reaction should go forward. It should be something that happens, and we should also see this voltage. Determine the cell potential for a spontaneous reaction between magnesium and bromine. Actually, we'll do it for, I'm going to get rid of this one, just to show something. Let's do between iodine and bromine. Okay, so iodine, what you do is just first write down the reduction potential. Now, if you can read off the table and determine the cell potential that way, that's fantastic. But if you can't, you want to write it out this way first, and just don't miss anything. This will allow you to, or you won't miss anything if you do it this way. So don't make any jumps unless you feel confident that you can do that. So make sure you get this right. So this is plus 0.54 volts, and then we have plus 1.07 volts. The book is just bent here. Just make sure they line up. Okay, now, the reason I wanted to do this is because they're both positive for their voltage. So it looks like, well, since E cell has to be positive, we could just add these up. Well, if you added them up, you'd just have 4 electrons on the reaction side, on the reactant side. And so the electrons wouldn't go away. That can't happen. What that says is that the electrons came out of nowhere and they just disappeared. They weren't, you know, say, well, that's possible, right? I mean, it's balanced, right? Yeah, it is balanced, but then those electrons came out of nowhere. So, you know, say you can't do that. The cell reaction has to have the electrons coming out of one species and going into another. By adding them up this way, you're saying the 4 electrons came out of space, and you could say, yeah, you could certainly set up a reaction that way in a vacuum, maybe in the gas phase, but it wouldn't work the way that it's supposed to here. So one of these has to be flipped. Since they're both positive, you flip the one that is the smaller number. So I'm going to do that. We have 2I. This becomes the oxidation. This becomes minus. So we have to go from having the 2 positive values. You're going to have to make one negative. You make the smaller one negative. So overall, it will be a positive value. So your overall, though it doesn't ask us for this, note bromine is a liquid and the iodine is a solid. So note that since you'll have to put the phases in, you need to get the correct phase. And that is the deal.